Hey guys, today we're going to solve LeetCode number 701, insert into a binary search tree. So we're given the root node of a BST and the value to insert into it, and then we need to return the root node of that binary search tree after inserting the value. And yeah, remember that we do not need to keep the binary search tree balanced or anything like that. We just have to find the position where we can add the new value and just add it in. Okay, so the first thing that you want to do is you want to create the new tree node that you're going to use to add it to the binary search tree, because here we just have an integer, right? So we want to make that into a tree node. And now we have two cases. Either we do have a binary search tree, and if we do have a binary search tree, then we are going to have to return the root of that binary search tree later on. And the other case is when the tree given to us is null. And if the tree given to us is null, then we just need to return our current new tree node, right? So if we have no root, just return the new tree node. So this is basically the edge case. And now we need to do the actual work where we actually insert the new tree node into the binary search tree. And so how we do that is we keep two variables. The first variable is the cursor that traverses the tree. So we're going to use this cursor to do kind of like a binary search to get to the position where we need to place the new tree node, to insert the new tree node. And then we're also going to keep a previous. So this kind of lags behind this cursor. So initially it's null. And then for every move that the cursor does, it follows it just one step back, right? Okay, and now we're going to use a while loop. So while our cursor is not null, so while our cursor is still on a node of our binary search tree, what we do is, first of all, we update our previous, because remember that we want this value to lag behind the cursor. And so since we're going to move our cursor further down the tree, we want to save the current value into previous, right? And then what we do is we check if the current value of the cursor is less than the value that we want to insert, then we want to move to the right. But else, so if the cursor value is actually greater than the value that we want to insert, then we want to move to the left, right? So you can like try it. Like here, for example, the cursor is originally 4 and you want to insert a 5. So it would be pretty stupid to go to the left, right? You know that you want to insert to the right of the root. And that is kind of the same thing, just on the subtree rooted at this node. So it's just the same thing all over again. So like here, we have this 7. This is greater than our value. And so we would want to go to the left, right? So that would be what we'd have to do if this tree was continuing. Okay, and yeah, we just keep doing this until our cursor becomes null, meaning that we were on a leaf and we just went one level deeper. So, but fortunately, we do have our previous value, which is still on that leaf, right? So what this does is it sends cursor off to null, but it keeps previous so that we still have the reference to the leaf where we need to add our new tree node, right? And so yeah, that's just what we can do right now. So we can check if the previous value, which is the leaf value, is greater than the value that we want to insert, then we want to put our new tree node to the left, just like here, right? But if it is less than the value, then we want to put it to the right. Like if we wanted to insert a 9, then we'd want to put it in the right of the leaf with value 7. In this example, obviously. So yeah, else just put it to the right. And that's it. Technically, this solution is O of n, where n is the amount of nodes in the tree, because technically you could have a tree that is like a linked list. But on a balanced tree, this is log n time complexity. And the space complexity is O of 1 because we're not using recursion. So yeah, that's it for me today. Thank you for watching and bye.